All right, so let's take a look at the warm-up here. All right, so the warm-up is just doing a little bit of matrix vector multiplication. So we're just going to go through this one real quick. A couple ways we can do this. One way is to think about the linear combination of the columns of the matrix technique. So this would be 1 times that first column plus 2 times that second column. And the result would be the vector 1/2, 1. Any questions about the first one? Second one, we'll do maybe the row vector operation. So in that case, we will take 1, that product, plus 2 times 0, which is 0. And the second one will be 1 times 0, which is 0, and 2 times 1, which is 2. We'll add those together to get 1, 2. And the last one, maybe we'll go back to the linear combination technique. I'm really adding the vector 2, 0, plus 0, 4. That's 2 times the column 0, 2. And this one will be 2, 4. All right, any questions about those calculations? All right, just kind of a nice, relaxing, easy warm-up today. A couple things to point out, though. What's special about the second case here? It's the identity matrix. So when I take this special matrix, we're going to call it the identity matrix, and you see maybe a little bit of it in the reading in the text, and we're going to talk a lot more about it later as well. We take this thing times some vector, what was the result? Just that same vector. Absolutely. The identity matrix is kind of like the 1 of matrices. When we multiply a number by 1, we just get the same number back. It's kind of like that with matrices. So this is the 1 of matrices. We're going to call that the identity matrix. And here specifically, it's a 2 by 2 identity matrix. What about the other ones? Do we see any kind of patterns developing in these other products? Maybe see any other patterns.
The others are basically just multiplying everything by 1/2 or 2.
Absolutely. The way these matrices are set up, the net result on the vector, this vector started at 1, 2, ended up to be 1/2, 1. It's kind of like I just took each of the components and multiplied it by 1/2. The second one, I started with the vector 1, 2. I ended up getting the vector 2, 4. It looks like I just multiplied each component by 2. So in this case, these special matrices look like they're doing a very simple operation, these vectors. And we're going to talk a little bit more about that later in the class. All right. Moving forward here. Our goal is to take any questions you might have from the previous section, any questions from the homework or from anything else. After that, we're going to get into section 1.8. We'll talk about linear transformations. There's going to be a whole lot of definitions associated with that, so hopefully you read through the section. We can just go through those and make sure that we're comfortable with the definitions. After that, we're going to talk about the key characteristics of linearity, and then hopefully we'll have some time for some Mathematica applications. So any questions about what we want to do today? Yep. Depends on how far we get today. So ask me that question again at the end of class. I'm going to try to have them once a week. So it'll either be today or it'll be on Tuesday. So please have it tomorrow, I guess. That's probably what everybody's saying, right, Stan? Running over the long break. Any other questions from the homework or any problems? All right. This Pearson homework has saved me a lot of class time, I'll tell you that much. All right, so from the reading, some of the big ideas. We need to be able to know the definitions of linear transformation. There's a whole bunch of associated definitions with that to identify the domain, codomain, image, and range of a transformation. These are all ways we characterize our transformations. After that, we need to know the properties that must be satisfied for a transformation to be linear. So we have transformations as a big process, a big idea. And then we have specifically linear transformations. We want to distinguish between those two things. So to start off, what is a transformation? So a transformation is a mapping from one space to another space. That's one way to describe it. And as you'll see, there's a lot of ways to describe transformations. It's almost like the rest of linear algebra, right? It's another way to describe something we're familiar with. So as an example, a function is like a transformation. Here's a function. And what this function does is it takes some input value. It takes some x that you put in, some input, and it maps it somewhere. It tells it where to go. It maps it to some function value, 2x minus 3 in this case. That's the output that we would get out from this function. And so, and again, I'm kind of talking through this, but I'm also going through some of the notation as well. So for instance, specifically, this would take the value 1 and map it to where? Negative 1. It's taking an input, it's mapping it to a specific output. And so that's what a transformation really is. Now the other thing we have to be aware of is what are our inputs and what are our outputs. So for instance, for this specific transformation, what are our inputs? What are all the possible inputs that we could use here? What could we put into our function? Any real numbers. There's really no restrictions here, just any real number. And then we look to the output and say, what are the outputs that we could possibly get out? In this case, also any real number. So we say this is a function is a mapping from the set of real numbers to the set of real numbers. So it's mapping from one space to another space. Okay? In this case, it's a basic space, so we don't really think about it that much. But that's really what it's doing. It's taking real numbers and mapping the other real numbers. In fact, we could change this a little bit. If I looked at this one, for instance, if I change a little bit, what are my potential inputs here? What's that? Well, I guess we should probably be careful, right? In some sense, we predefine some of our restrictions here. So if we're working with real numbers, we'll say we can use any real number to input in here. But we say, what are the possible outputs here? Positive values, right? We're not going to get any negative values for that. So we're going to have to talk about that kind of distinction as well. All right, so why are we talking about functions in this linear algebra class? Well, when we think of that way to describe transformations, well, then we can think of matrix multiplication as a kind of transformation. It's taking this value, A, is acting on some vector. It's acting on this vector, and it is mapping it to some other vector. Now, when I write AX over here on the right-hand side, I'm saying it's mapping X to B. But AX equals B, so I'm just writing it as AX here. That's me writing f of X, sort of, right? So it's mapping. And so we have all those same ideas we had before. Where am I taking values from? Where am I mapping my values to? Those kind of questions. So in this case, the domain is basically where our inputs live. So in this case, where do our inputs live? It's not R anymore. What is it? What's that? Not in A. A is the thing that is taking our inputs and sending them somewhere else. So if I want to kind of play with this thing, now maybe I want to do some samples like I did before. Last time I took 1 and I saw where it mapped to. So let's try that. What am I going to take to test this thing? What am I going to put into my equation here? I have some matrix A, and I got to throw in some x value. So give me an example of an x vector.
1, 2.
1, 2, right? Absolutely. 1, 2. How come not 1, 2, 3? I can't put that in here, right? I couldn't do the multiplication, so it has to be 1, 2, 2, 4, something like that. So that's the input, is this x value. And it's a two-dimensional vector, so my input values, my space where all my inputs live, is R2. And that's where my inputs live. Now the codomain is where all my outputs live. So where do all my outputs live here? This example. Absolutely, but what is AX? So for instance, we said I have 1, 2, 3, 0, 1, 1, and our example was use 1, 2. So when I do that multiplication, I'm going to get some output. All right, I put my input in. There's my input into my transformation here. And I do the operation. I'm going to get 1, 3, 1 plus, multiply that next column by 2, 4, 0, 2. So I'm going to get 5, 3, 3. So this is my output. Where does my output live?
B.
That output is B. B is the vector I'm getting. But what's the space that that thing lives in? Is that an R2?
No.
Where is that? R3. So I'm plugging in two-dimensional vectors, and I'm getting out three-dimensional vectors. So in this case, A is a mapping. It's a transformation that maps R2 values to R3 values. It's a mapping from R2 to R3. And so some of this notation is the stuff we're really going to need here. Now the next little term we have there is the image. The image, and we say this as the image of X under A is B. That's how we kind of describe this. The image is the output. It's whatever you get from plugging in X. You take X, you apply some transformation A to it, and this is the image. And we'll talk about this sometimes as the pre-image. It's kind of like we have a projector screen, right? And I'm going to put something into it. There it is. There's my hand. Right? This is the input. The output is going to be the image that's displayed over here. Okay, so it's the specific output from a specific input. So in this case, the image of 1, 2 under A is 5, 3, 3. Any questions about the image? And then lastly, the range is the set of all images. Images. So let's talk more about the range here. The set of all the images. How would I describe that? How would I get that? Set of all the possible images. All are possible solutions, right? It's any B that I could get if I'm doing this multiplication. For any value of X that I can pull from the domain, the collection of all the possible outputs is that range. But I actually have another name for that, right? I could just say that's the span of the columns of A. Because for any value in here, this is just saying take some linear combination of these two columns. If I take them all, I'm taking the span of these two columns. And so another way to describe this range is the span of the columns of A. So I said all my outputs, the codomain there is R3. Is that also the range? What's the difference between the codomain and the range? They seem to be the same, right? I mean, R3, my outputs R values in R3. But the question is, the codomain is all of R3. Can I get to all the possible values in R3 using a linear combination of those two columns? Can I get to them all? I can't in this case. I can see that because I only have two of them, and I really need 3 vectors to get to anywhere I want to in R3. Just like I need 2 linearly independent vectors to get to anywhere in R2, I'm going to need 3 to get to anywhere in R3. So there are some vectors in R3 that I can't get to by adding some linear combination of these two. Okay? So the range is a little different than the codomain. The codomain is the big space where all the outputs live, and the range is specifically the part of the codomain that I can actually get to using certain x values, right? It's the ones I can actually get to. Questions about that? Okay, and one quick thing to note here. So this represents a mapping from R2 to R3. Now just kind of pair that up with the matrix notation. This is the matrix that's 3 by 2, a 3 by 2 matrix. Now the dimensions of the matrix also kind of tell us exactly what the size of the thing we can multiply it, right? Like the size of this vector has to be the same as the number of columns here, otherwise we can't do the multiplication. So the number of columns. The output has to be the same as the size of the columns, or the number of rows. Right, so this size and this size are really defined when we look at this matrix A. So that means also these two spaces should also be clear. And so you have to be a little bit careful because it's kind of backwards, right? A is a 3 by 2, and it's mapping from R2 to R3. So just be aware that it's a little backwards there, right? And when you get stuck, don't try to memorize the order or that it's backwards. If you get stuck, draw the 3 by 2 matrix and say, what's the vector here that I would multiply it with? And that will tell you where those inputs live. All right, any questions? A lot of terminology, a lot of concepts here. All right, let's try some. All right, here's a matrix A. Thinking of this as a transformation, describe the domain, the codomain, the image of 3, 1 under A, and the range of A. Feel free to check your answers when you get them. Feel free to talk about it. Point is to make sure that we're comfortable with these definitions before we move on. And remember, check your answers, right, with your neighbor, or also, if you think this is the size of the domain, grab a vector, put it next to A, see if you can do the multiplication. See if a sample works. A lot of blanks, but not a lot of talking. Feel free to talk. Feel free to ask. Raise your hand if you have a question. right, I'm going to pretend like I'm going to do a matrix equation here. How many x's do I have to put in here to make this thing work? 2, right? An x1 and x2 has to be the same as the number of columns. So that means my domain is what?
X1, X2.
That's R2. It's a set of all two-dimensional vectors. R2 is a set of all two-dimensional vectors here. And that's what I'm plugging in. I have to have two-dimensional vectors to put into this equation. So I do this multiplication, and what do I get over here? I'll write this with b's, b1, b2, b3, however many I need. How many b's am I going to get over here? 3. I'll get b1, b2, and b3. Because to do that multiplication, I'm just really taking a linear combination of these two things. Those are both three-dimensional columns. So if I add two three-dimensional vectors together, I'll get a three-dimensional vector. So that means the codomain of A is what? R3. So A is a transformation. It's taking vectors from R2 and mapping them to R3. That's what it's doing. It's a mapping. Now the image of this specific vector, 3, 1, under A, just as if you put this one into the transformation, where do you end up? If you start at 3, 1 and you hit it with A, what's the result? So let's do that. 1, 3, 0, 2, 4, 1 times the vector 3, 1. I will get 3, 9, 0. That's 3 times the first column, plus 1 times the second column. Looks like I get 5, 13, 1. This is the image of 3, 1 under A. And the last one is the range of A. This one's a little trickier. Can we get to all of R3? I can't. All right, so I have to have some way to describe this thing, some way to describe that output. It's really just a linear combination of those two columns. It's just this thing. It's x1 times 1, 3, 0 plus x2 times 2, 4, 1 for any x1 and x2. And so I guess what I'm asking for when I say describe the range here is, what does this thing look like geometrically? Is the range going to be a point? Is it going to be a line? Is it going to be a plane? Is it going to be all of R3? What's this output going to end up here? What's the range going to be? What does this linear combination look like geometrically? Plane. So it's going to be a plane. Any questions about that? It's going to be a common question to describe these solutions geometrically. Yep.
Is there ever a time where the domain's not going to look like that? The codomain will? It won't be R.
Well, R2 or R3?
Yeah.
Well, you could put restrictions on your domain. So there could be cases where you'd want maybe positive R values. This describes a transformation, not just the specific transformations that we're looking with matrices. Right? So we could talk about the domain of a function. Right? We've talked about that in the past. So we could also talk about complex matrices where there's complex values instead of just real numbers. And so there it might be C2 or C3. So there's a lot of other domains you can use as you generalize this idea. When we do matrix multiplication, it's going to be R2, R3, these things. Okay? Good question. Other questions?
The plane is in R3, correct?
Yes, this will be a plane in R3. So we can even kind of sketch this if we wanted to. We would have 1, 3, 0. So we have any kind of linear combination of that thing. So that's like a line that goes like this. So I could have this value plus 2, 4, 1. So that would be plus 2 in this direction, 4 in this direction, and up 1. So it would also be any linear combination of those values. So you'd get these and these. It would be that plane. Hard to draw in 3 space, but you could actually throw it in Mathematica and see a plot of that plane in 3 space if we wanted to. Any other questions? And once again, we can see that plane, one, because we can kind of see the vector addition, but also we essentially have two free variables when we look at this linear combination. So we have two independent variables, and a linear thing of two independent variables, and we have plane. All right, so now let's talk about linear transformations. So all that stuff we were just talking about applies to transformations in general. But now we want to talk about linear transformations as a subset of all the transformations. The transformation, or mapping, is linear if the following two conditions are satisfied. So these are the conditions for a transformation to be linear. Let's see the characteristics of linearity. And this is a very, very broad topic. And you'll see as we apply this definition to other more general transformations, that this allows us to take linear algebra ideas and transfer them to calculus and statistics and image processing, all these other fields, because we can show that certain transformations satisfy this thing. And so we use these characteristics to show that transformations are linear, and then we can apply our linear algebra stuff to them. So I might want to check if a certain transformation is linear. So for example, is the function 2x linear? If I think that this is a transformation where f is transforming x to 2x, is that a linear transformation? Now it looks like it. It's a line, right? So I might expect it to be linear. But I actually have to show it using these properties. So how do I show these properties are satisfied? Well, the first one says that if I take the transformation and act on a sum, it's the same thing as acting on the pieces and then adding them separately. We say the transformation preserves addition. It preserves vector addition. So it doesn't mean if you add first or you transform first, it's going to be the same in either case. So what this means is I have to say f of u plus v, two values. In this case, they're not vectors. In this case, they're number values because the function is mapping r to r. So I have to start from there and somehow show that this is the same thing as just this. So that's my goal. I start on one side, I see if I can get to the other side. So I have f of u plus v. What is f of u plus v?
That's u plus fv.
Not necessarily. In a lot of cases, it's not. So I can't jump to this step. I have a function. The function is f of x equals 2x. Right? So if I plug in an x value, I get 2 times that value. What's f of 1?
1.
2. Right? What's f of 3? If I plug in f of 3, what do I get? 6. What's f of y?
2y.
2y. What's f of u plus v? 2 times u plus v. Okay? I'm just taking that input, applying it in my function. I say, oh, wait a second. These are just numbers. U is just a number, v is just a number. I have this thing called the distributive property, so no problem. I can take 2 and distribute my 2 and say this is the same thing as 2u plus 2v. And then I say, wait a second. 2u, that's just f of u. Okay? And 2v is what? F of v. So it's exactly this. Therefore, I've shown that that first thing is satisfied. I do the same thing with the second property. I need to show that f of some constant times u is equal to a constant times f of u. So I apply my function definition. F of c times u should be 2 times c times u. These are all just numbers, so I know that by the properties of real numbers that I can switch the order and say this is c times 2u. But that's just exactly c times the function evaluated at u. So it's almost so easy it's hard. Right? Because you're not really doing a whole lot. You're just plugging in the function and say, yeah, I can do this. It does get a little harder But let's just show an example where one's not linear. What about f of x equals x squared? I really don't expect that to be linear. Well, let's test it out. First, I'll try to show that it preserves addition. F of u plus v, well, if I apply the function definition, that should be u plus v squared. Now, when I expand that out, I'll get u squared plus 2 times uv plus v squared, which is equal to, well, this piece is just f of u. This piece is just f of v, and that's not equal to f of u plus f of v because I have this middle term. So that first property is not satisfied here. Okay. So in general, in most cases, those properties don't work. They only work in special cases, and when we see those special cases, we call those transformations linear. All right, any questions about these? Good, and I have 3 for you. Try these 3. Show that these are linear, these transformations. So is multiplication by a matrix linear? I hope so, because that's what we want to do, right? But what about other transformations? What about the integral of a function? Is that linear? Is that a linear process? What about that last function? So you can go through and you have to show that those 2 properties are satisfied. All right, so I don't want to spend a whole lot of time on the first one because there is kind of a good way to show it. You know, if I was really trying to work through this kind of the long way, I would say, okay, this is the vector u1 and u2. This is the vector v1, v2. I know how to add vectors. This could be the vector u1 plus v1, u2 plus v2. So that means this is u1 plus v1 times the first column if I do the multiplication here. And then plus u2 plus v2 times the next column. And then I have rules about how I can distribute, because u1 and u2 are just scalars. So I can say this is u1 times this thing plus v1 times this thing. Do the same thing for the other side and regroup, and I'll get right back to what I want to get to. At the same time, I could go through all those steps and be really careful about this, but if you look back in your book at section 1.4, when they talked about matrix vector products, they tell some of the properties for this. And the properties they mention are this. They tell us that this property is true. And they also tell us that this property is true. So when we first learned about matrix vector products, they said, oh, by the way, these two properties hold, so you can use these properties when you multiply matrices to vectors. Well, what are these two properties? These are exactly the properties of linearity. Right? If I take the matrix times the sum, I get the sum of the products here. So before they said, oh, these two properties are hold, we're like, oh, great, that might help with some of my calculations. Now I can do a little bit of algebra. But it was more powerful than that. They were telling us at that time that this was a linear operation. So at this point, because we've already been told these properties are true, we could just apply them directly. We could say, yeah, this is true, and this is true. So great, it's linear. Okay. All right, what about the next one with the integral? First, we have to test out our first one. So I say, is the integral, so we need to show that t of f plus g, two functions, is somehow equal to t of f plus t of g. So what is t of f plus g? What does that mean? Our transformation is taking some input and mapping it to the integral of that input. So now my input is f plus g, so it should be mapping it to what?
Two f plus 2g. Yeah.
Okay, so my transformation is defined by this integral. Right? So f is my input, and essentially this is where I put the input. I'm taking some function, and after I hit it with the transformation, I'm integrating it. So if I put t of x squared, I'm putting x squared as my function. The transformation would integrate x squared. Right? If I said, what's t of cosine of x? Well, the result will be the integral of cosine of x, and I have to do the integration to find out what that is. If I say t of x squared plus cosine of x, the sum of two functions, the result will be to integrate those two functions. Integral of x squared plus cosine of x. So here that's what I'm saying. I'm saying the transformation of the sum of two things. So I put this in as my input, and what's my result here?
The integral of those two sides.
Absolutely, the integral of f plus g. Okay. Now where am I trying to get to? I'm trying to get to this side. That side just says, well, t of f is just the integral of f, and t of g is just the integral of g. I need to get from here to here. How do I do that? I can't tell if we're getting this, and oh, we don't want to say it because we're shy, or if we're not getting this. The only way I can tell that is by having a quiz. I certainly don't want to make us get pieces of paper out right now and be like, just write some things down, but I got to know if we're understanding this or not. Because this is tricky. It's function notation that sometimes we zip through quick. I need to know if we're getting this or not. So when I get to this, this is like saying the integral of x squared plus cosine. And somehow I need to say, is that the same thing as the integral of x squared plus the integral of cosine? Is that true?
Yes.
It is true. Why? We have a property, right? We have that property. The integral of a sum is the sum of the integrals. They told us that in Calculus 2. They told us those properties so we can do integrals. That's also telling us that it satisfies linearity. Okay? Now the other one would be the integral of, or the transformation of c times some function. Well, that's just the integral of c times some function. What do I do with constants when they're inside an integral? I pull them out. So this is c times the integral of f. but that's just c times the transformation of f. So integrals are linear transformations. We can think of integration as a linear transformation. So that means later on, you might be able to do some calculus stuff with some linear algebra stuff. It really extends our ideas of linear algebra to these other fields, because these other things are really just linear transformations in disguise. All right. The last one. F of x equals 2x plus 3. So if I take my transformation, so this is t that takes some x and maps it to 2x plus 3. If I take t of x plus y, the sum of two things, I plug that into my function. I get 2 times x plus y plus 3. I distribute the 2. I get 2x plus 2y plus 3. Well, let's see, 2y plus 3, that's the same thing as t of y. Is this thing equal to t of x? It's not. This thing is not a linear transformation, even though it's a line. Weird, right? So even though we have a line, a linear function, it's not a linear transformation. You have to be a little bit careful about distinctions here. For us, linear transformation are only lines that go through the origin, and where it doesn't have this extra 3 that kind of messes things up. Okay? All right, questions about linear transformations?
So what you're saying by that is that if you shift it free or any which way, then it's not a...
It messes up the linearity of the transformation. They have a special name for that because it's a line. It's not quite linear because of this shift. We could actually shift it back down and make it linear. So they have a special name for that group of transformations. They call them affine. So that would be an affine transformation. Yep. So, scaling it back because that's the origin. Yep, absolutely. Okay. All right, so that's linear transformations. Once again, it's not a hard topic once you get it, but it's the notation that's weird. It's getting back to that old function notation that we kind of always hated in pre-calc and calculus, and luckily then we were kind of able to avoid it. We didn't have to write it out so symbolically most of the time. But here we need more of the symbolism. So it's a little tricky to get used to that notation. Okay, we're going to also talk about special transformations from R2 to R2. And we're going to talk about this in terms of nice matrix multiplication. So it turns out, sometimes when we have linear transformations, we can represent those as matrix multiplications. So it turns out if I want to do this transformation from R2 to R2, if I want to take a vector and essentially scale it, I'll call it a contraction if it's shrinking. I'll call it a dilation if it's expanding away from the origin. It really depends on the size of this value. But I can represent that as a matrix times a vector. So I can find some matrix times, for instance, 1, 2, that will turn it into 2, 4 or 3, 6. It will act just like scaling that thing. Have we seen that before? When did we see that? In the warm-up, right? So it turns out our matrix is going to be specifically R, 0, 0, R. That's what all my matrices look like in the warm-up. So if I take this thing, it will end up looking like R times x1, x2. And of course, that's easy enough to prove. We just actually write out the multiplication and we'll get to the step. So this lets us tweak points. All right, so why is that useful? All right, so there's other transformations too. So this would be a contraction or a dilation. And the next section, we're also going to talk about some other ones. For instance, a rotation. A rotation has a special form. It has a bunch of trig functions, and it actually looks like this. But this is going to be another transformation for us, is this kind of matrix. And we have the cosine of t, sine of t, negative sine of t, cosine t. We'll talk more about this in the next section. But this is one example of a transformation using a matrix multiplication. So what happens? I start with a point. Here's my point 1, 2. And then I have this transformation matrix. Could be a dilation, could be a contraction. In this case, it's a rotation. So what happens when I take my point and I multiply by my matrix? I have my matrix here. This is the rotation specifically of 90 degrees. All right, so I put in a specific value. I'm going to take that matrix times my point. And there's my output, negative 2, 1. It took 1, 2, and it mapped it to negative 2, 1. Now, was that actually a rotation of 90 degrees? Hard to tell unless we look at it. So those are those 2 points. I started off with 1, 2, and I rotated it over here to the point negative 2, 1. And I drew the little vectors in there so we can kind of see this really is 90 degrees. Now the nice thing about this matrix is I can really scale it as well. It doesn't have to be pi over 2, and so it's very easy for me just to make that a function t and say as I multiply that point by that matrix, I'm getting all the new points for any spot along that rotation. So instead of using that static matrix, I just put my matrix as a function of how much I want it to rotate. So this is this matrix times my point, and it's giving me my new point. So it lets me find all these different points along this rotation, which is a very nice thing to do. I don't have to calculate the rotation here and here and here. I can represent the process of rotating as a linear transformation and turn it into matrix multiplication, which is a very fast process. Any questions about that? Let's tweak it a little bit. Let's not use that matrix. Let's do something different. Let's do this matrix. T 0, 0, T. All right, that's that contraction dilation thing. So right now I made T 0, so it didn't do anything here. Let's put in the value of 1. All right, so now I'm right on the point. Now what happens if I multiply my point by something bigger than 1? It's dilating, it's blowing up away from the origin. What happens if I multiply by something smaller than 1? It gets closer and closer to the origin. All right, so in this range, we'd have a contraction. I'd be contracting towards the origin, and here I'd be expanding away from it. Now, I can get all those things very quickly from this matrix multiplication. All right, now let's do a kind of an application thing here. All right, so I'm going to go back to that rotation idea. I'm going to do a couple of mathematical real quick commands here. Big smile. Okay, so what I've done here is I've taken my webcam, it's taken a picture from the webcam, I imported this picture from the webcam, and I binarized it. That means, normally when there's a picture, at every little point in this little grid, it's going to assign it a color value. Right, it's going to be RGB, a three-dimensional coordinate here. Well, I don't want to work with that. I want to work with something easy the first time. So now I made it black and white. So it basically takes all the dark points, makes them black, all the light points makes it white. It gives each pixel here, its position, a value of 0 or 1. And so that's what it did. So what I have is a whole bunch of coordinates with a 0 or a 1. Now I do this thing. This says pull all the coordinates that have a value of 0. I did that. And I can plot those values now very easily just by looking at plotting all those coordinates. And when I plot all the coordinates with a 0, I get my picture back, right? But now they're just a list of points, so there's no reason I couldn't take my rotation thing here, rotate it by, say, pi over 2, and multiply all those points by that matrix. And hopefully get something that will work. On the wrong side here. Let's tweak this a little bit. And rotate my image. I don't have to rotate it all the way. I could rotate it like this. I can do whatever I want to it. All right, this is how I can manipulate some images. So for instance, here's my picture again. And I can tweak it all like this. All right, rotate it however I want. It doesn't have to be a rotation matrix though, right? It could be that same matrix we did before. So it could be T, 0, 0, t. In which case I would be doing a contraction or dilation. Now the other thing we can do with this, if I did another kind of version here, so once again I got to take a picture. I'm a bad picture taker. Lame smiles all the time. So this side, instead of binarizing it, I put it into a grayscale. So it gives me a value between 0 and 1 to define the grayness of this thing. I have some stored values in here. And so the thing I want to stress with this case, it makes it a little different and a little more useful, is that I did this thing. And so it was a little tricky for me to get the values out because I had this weird gray value between 0 and 1 for all these different spots. And the way that I did this mathematically wasn't the most efficient way. And so when I ran it like this, it took a really long time to process. It took a really long time to go back and for each different point, put this new gray value in to construct my picture back here. It took forever. In fact, when I just did it originally, I wasn't patient if I couldn't wait. So what I did instead was instead of looking at every single point, I skipped and did every other point. And then it went much faster. So you saw how long it took to do this one. If I change those values to 4, I do every fourth one, it would go much faster. There would be little gaps, though, in the picture of whiteness, of blank spots. But it depends on how much you contract or dilate it, you won't see those things. So this is one way you can think about image compression, is you have a big image, and then you can just skip every other pixel or associate every pixel with the previous value, and then you can adjust the contraction dilation to still get a good appearance of a picture. So image processing definitely relies on linear algebra quite a bit. And we can do some of this image processing just with the stuff we already know about linear transformations. All right, any questions about that? Okay, that's all I got for today. No quiz tomorrow. Just kidding. Test tomorrow.
Don't get any bright ideas.